This is section 1.3. Today we're going to cover two of the most important definitions in this class, linear combination and span. Let's start with vector arithmetic and descriptions of vectors. So the set Rn, and if you're writing this longhand, it's double back R, like that, not R. So this indicates the set of real numbers. And so Rn is the set of ordered n tuples of real numbers. For example, R2 is the set of all vectors in R2. So it's vectors that look like AB, where A and B are in R. And this backwards E means in. You can use parentheses for vectors or brackets, and that's it. Square brackets or parentheses. The vector ABC with parentheses lying on its side and commas is a space-saving notation for this vector here. So you can't use A, B, C with square brackets and no commas because that means the matrix that has one row and three columns. So if you want to indicate you have a column vector, you have to use parentheses with commas. And we'll do that when we get to chapter 6. But for now, we're going to stick with the column vector notation. Addition and scalar multiplication. Let's talk about those two operations. This is done component-wise. So for example, if u is the vector 2, 1, 2u, what we do is we multiply each entry of u by 2, 4, 2. Geometrically, what that does is it stretches the vector u by a factor of 2. So here's 2u. U plus v, we're going to add component-wise. That means we add across the top, we add across the bottom to get 2, 4. So that's this vector here, and geometrically you want to think of that vector as the diagonal of the parallelogram spanned by u and v. The next one, C, u plus w. Well, u is in R2, w is in R3, so you can't add a vector in R2 to a vector in R3. They have to have the same number of components because we add component-wise. So that's just nonsense. Subtraction, again, just subtract across the top, 2, and then 1 minus 3 is negative 2. That's right here. And geometrically, we want to think of that as u plus negative v. So negative v is the vector v going in the opposite direction. This is negative v. And u minus v is the vector, if we think of it as u plus negative v, it's the diagonal of the parallelogram spanned by u and negative v. Okay, properties. These are just basic properties that you would hope to be true, like commutative, associative. If you add 0 to u, you get u. Now, is that 0 the number or 0 the vector? Well, it's got to be 0 the vector because let's say u is in R2. Let's say u is 1, 2. If we want to add 0, it wouldn't make sense to say 1, 2 plus 0 because I need to add component-wise. So 0 has to be a vector in R2, 0, 0. We add, we get 1, 2, which is u again. Same with this next one, u plus negative u. Well, if I add u to negative u, that would be 1, 2 plus negative 1, negative 2. I don't get 0 the number. I get 0 the vector. The next two are some distributive properties. This is another form of the associative property, and 1 times u is u. All right, here's our first big definition. If v1 through vp are vectors in Rn, a linear combination of those vectors is a vector of the form c1v1 plus c2v2 plus dot 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 plus cpvp, where the c's are called the weights, and those are real numbers. Now you can say this one of three ways. You can say where C1 through CP are real numbers. You could say where C1 through CP are contained in R, or you could say where C sub I is contained in R for all I. Those are three different ways of saying the same thing. Pick one version and memorize it because you will be tested on it, and don't get sloppy in your definitions. For example, if you go C1v1 plus C2v2 dot 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 CP, VP. That's not right. You need a plus sign here, then dot, 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 and a plus sign here. So you really have to memorize these exactly the way they're given. Okay, so let's talk about linear combinations. Given two vectors, can we write another vector as a linear combination of those two vectors? Oftentimes we can do it by inspection. So in this case, 7, 0, if you look at this long enough, you'll say, oh, that's U plus 2V. The next one's super easy. You can always write the 0 vector as a linear combination of other vectors. This is 0u plus 0v. But in general, given a vector b, like this example, and two other vectors, v1 and v2, it's not so easy to write b as a linear combination of v1 and v2 by inspection, just doing it in your head. So we need a better way. This is the better way. So first of all, in the definition of linear combination, I'm going to switch the c's to x's so that this looks more like our linear system with variables x1 and x2. So what we seek is x1 and x2 such that x1 v1 plus x2 v2 is equal to b. That's what we want. So the first step, I wrote that out. I replaced v1 with what it is, v2 with what it is, and b with what it is. That's a vector equation. That's true if and only if, in the next step, I just distributed the x1 and the x2 into the vectors. And that's true if and only if, in this last if and only if, what I did was just expanded this as a linear system. But we know how to solve a linear system, right? We can reduce the augmented matrix. So what we want to do is find x1 and x2 such that we have a solution to this augmented matrix. So we've turned a hard problem into a pretty easy problem. So let's start reducing. The first thing I'm going to do two row operations at once. I'm going to replace row 2 with 2 row 1 plus row 2. I'm going to replace row 3 with 5 row 1 plus row 3. That will kill off the -2 and the -5. So the top row stays the same. And then my second row is 0, 9, 18. And my third row is 0, 16, 32. Now I'm going to do two more operations at once. Normally I don't, but if they're easy operations, I do. I'm going to take 1/9 row 2 and 1/16 row 3. So 1, 2, 7. 0, 1, 2, 0, 1, 2. Now I'm going to replace row 3 with negative row 2 plus row 3. I'm trying to get to echelon, well, I want reduced echelon form. So I'm almost at echelon. 1, 2, 7, 0, 1, 2, 0, 0, 0. That's echelon. But I want to go one step further. I want reduced echelon. So I'm going to replace row 1 with -2 row 2 plus row 1. And I get 1, 0, 3, 0, 1, 2, 0, 0, 0. Okay, the last line doesn't give us anything. It just says 0 equals 0. But starting at the bottom, remember you always start at the bottom. So there's two variables because there's two columns and then the augmented column. Starting at the bottom, x2 is 2. And then I go up, x1 is not free, it's 3. So my solution is x1 equal 3, x2 equal 2. But I was asked to write b as a linear combination of v1 and v2. And so circling that wouldn't be appropriate. That's not a linear combination, right? So we need to know what to do with that answer. Well, look up here to the circle. What we were looking for is an x1 and an x2 such that x1 v1 plus x2 v2 was equal to b. Well, we found x1 and x2. Now we need to use them. So x1 is 3, so 3v1, and 2v2 is b. That's what we want to circle. b is a linear combination of v1 and v2. Or you could put b on this side. That's fine too. So make sure you answer the question appropriately to how it was asked. Okay, so that whole long example was to illustrate this theorem. This theorem says that the vector equation x1 v1 through xn vn, the addition, equals b, has the same solution set as the linear system with the augmented matrix that has the v's in as the columns, and then you augment with b. So b is a linear combination of the v's if and only if, when you reduce that augmented matrix, you get a consistent system. So let's see an example where that doesn't happen. So write b as a linear combination of v1, v2, v3. It's hard to do mentally. So what we're going to do is reduce the matrix, the augmented matrix, with our V's as the columns and then augment with B. So 1, 0, 0, 0, 5, 5, 2, 4, 4, and then negative 5, 1, 3. So what I'm going to do, 0, 5, 4, 1, I'm going to take row 3 and replace it with negative row 2 plus row 3. And I get 0, 0, 0, 2 here. Then I can stop because I have a 0, 0, 0 B row. And we know whenever we see that, we have an inconsistent system. So B is not a linear combination, LC, of V1, V2, V3. If it were, we would have been able to solve the system for the weights. Okay, next big definition, span. The span is the set of all linear combinations of V1 through Vp. So you start with P vectors in Rn, you look at all the linear combinations, it gives you the span. That's the English definition. I want you to memorize the math definition, which says it's the set of all. So the squiggly brackets read set of all, C1V1 plus ... CPVP, such that, that's the straight bar, C sub I is contained in R. All right, so the following theorem just restates the theorem on the previous page in terms of this new span definition. So if V1 through Vp and B are all in Rn, the following are equivalent. We're going to have a lot of those, and it's TFAE. So usually I'll just write TFAE. I won't write out the following are equivalent. B is a linear combination of V1 through Vp. B is in, that's what the backwards E means, in the span of V1 through Vp, because the span is the set of all linear combinations. And we know that that is equivalent to, if you try and solve the linear system with the V's as columns augmented with B, it's consistent. So geometry of span. Suppose you have two vectors in R3. They're non-zero, and V is not a multiple of U. You can look at two sets. The span of U is going to be all the multiples of U, because it's the set of all CU such that C is a real number. That's just multiples of U. That's going to form the line going through the origin in U. As long as U is not a multiple of V, if you look at the span of UV, that's the set of all linear combinations of U and V. So this is going to be the set of all CU plus BV such that C and B are contained in R. That's going to form the plane going through the origin and through U and V. So let's look at a particular example here. Given a plane, and we're given U and V lie in that plane, W1, W2, W3 all lie in that plane. We want to write the W's as linear combinations of the U's and the V's. So let's start with an easy one. Let's start with W2, because W2 just goes in the opposite direction as U. U goes 1 unit out, W2 goes negative 1 unit out. So W2 is just negative U. All right, what about W1? Let's form the parallelogram with diagonal W1. I'd have to go up here to 2U and then go over. So since W1 is the diagonal of the parallelogram spanned by 2U1 and V, we can write W1 as 2U1, just 2U plus V. And then for W3 is over here. Well, that's going to be U. This is negative 2V. So W3 is the diagonal of the parallelogram spanned by U and negative 2V. So this is U minus 2V. Okay, so let's do one more example. Let A be the matrix with columns A1, A2, A3. So this is column A1, this is column A2. So A1 is this vector, 1, 0, 2. A2, and this is A3. I think this is pretty obvious, but I'll just write it out. Like A1 is the vector 1, 0, negative 2. And B is this vector, and W is the span of A1, A2, A3. So the first one, show that A1 is in W. So show that A1 is in the span of A1, A2, A3. Well, the span of A1, A2, A3 is the set of all linear combinations of A1, A2, A3. So what we have to do is show A1 is a linear combination of those three vectors. So that's easy. A1 is 1 times A1 plus 0 A2 plus 0 A3. That's a linear combination of A1, A2, A3. So that shows me that A1 is in the span of A1, A2, A3. How many vectors are in W? Infinitely many. W is the span, which is the set of all linear combinations of these three vectors. Well, for every weight, you get a new linear combination, every set of weights. So there's going to be infinitely many vectors in W. Whereas there are only three vectors in the set A1, A2, A3. Is B in the set A1, A2, A3? Well, B is in that set if and only if B is one of those three vectors. No, B is clearly not one of those three vectors. So no. But contrast that with the next question. Is B in the span of A1, A2, A3? So those are two very different questions. One we can do just by looking. Is B one of those vectors? No. The second question, the answer is yes, and the way to answer that is to figure out that B is a linear combination of A1, A2, A3, which means we need to do some computation. So we want C1, C2, and C3 such that this equation's true. So what we need to do is reduce the augmented matrix where the A1, A2, and A3 are our columns. Those were the V's before, now we're calling them A's, and B is the augmented part. And instead of calling the weights x1, x2, x3, I'm keeping them c1, c2, and c3. First step, I want to kill that -2. So I'm going to replace row 3 with 2 row 1 plus row 3. You might want to pause the video, make sure you can do this reduction to reduced echelon form on your own, and then watch me do it. So 1, 0, -4, 4, 0, 3, -2, 1, 0, 6, -5, 4. Work smart, not hard. This needs to be a 1 eventually, but if we turn it into a 1 now, we're going to get fractions. Let's use this 3 to kill off this 6 first, because that 6 has to go. So I'm going to replace row 3 with -2 row 2 plus row 3. So row 1 stays the same, 1, 0, -4, 4. Row 2 stays the same. Row 3 becomes 0, 0, -1, 2. All right, now I could use that -1 to kill what's above, but first I'm going to turn it into a 1. So I'm going to take negative row 3, 1, 0, -4, 4, 0, 3, -2, 1, 0, 0, 1, -2. Okay, so I've done the forward phase. I'm in echelon form. Now I need to start going backwards. And I need to go backwards in order. First, I'm going to kill that guy. So I'm going to replace row 2 with 2 row 3 plus row 2. 1, 0, -4, 4, 0, 3, 0, -3, 0, 0, 1, -2. Okay, now I'm going to come down here. I'm going to replace row 1 with 4 row 3 plus row 1. And that's going to give me 1, 0, 0, -4, 0, 3, 0, -3, 0, 0, 1, -2. Okay, just one more step. Take 1/3 of row 2. 1, 0, 0, -4, 0, 0, 0, -2. All right, so we can read the solution right off of there. C1, well, I like to start at the bottom. C3 is -2, C2 is -1, and C1 is -4. But our job was to write B as a linear combination of A1, A2, A3, so we need to answer in the right way. B equals -4 A1 minus A2 minus 2A3. Now, if this were a test and I had some extra time, I would do a safety check. I would say, okay, is B really -4? I would put in A1, 1, 0, -2, then minus A2, 0, 3, 6, minus 2A3. A3 is -4, -2, 3. And I would distribute the -4, and I would combine this as a single vector and check, is it really equal to B? Is 4, 1, -4 really the same as this vector? So that's how you can check your answer. And that's the end of this section.